Algorithm design. Unraveling the core strategies behind efficient solutions. Designing algorithms is at the heart of computer science, enabling software engineers to solve complex problems efficiently. It's an art that blends creativity with logic, where every decision affects performance and scalability. From sorting a list to optimizing routes in logistics, understanding core algorithm design principles unlocks powerful solutions. This guide dives deep into key strategies and techniques shaping modern computational challenges. The art of decomposition, breaking down complexity at its essence. Algorithm design thrives on decomposition, splitting vast problems into smaller, manageable components. This approach allows developers to focus on individual pieces before integrating them into complete solutions. A classic example appears in recursive problem-solving methods. By dividing tasks into subproblems similar to original ones, programmers can create elegant, reusable code structures. This technique reduces cognitive load significantly. Instead of grappling with monolithic functions, designers work with focused modules that can be independently tested and optimized. Modularization, segregating functionalities, enables easier maintenance and updates without disrupting entire systems. Reusability, well-designed decomposed algorithms often find applications beyond their initial purpose, promoting efficient coding practices. Detailed analysis shows that modular approaches lead to faster development cycles by allowing parallel progress across different components. The benefits become especially pronounced when debugging becomes necessary. Isolating faulty segments simplifies troubleshooting substantially compared to holistic inspection. Greedy algorithms, making the best choice locally. One prominent strategy involves greedy algorithms which make locally optimal choices aiming for globally optimal results. While effective in many scenarios, they sometimes fail spectacularly due to poor long-term consequences. Classic applications include graph traversal techniques like Kruskal's algorithm for minimum spanning trees. These implementations prioritize immediate gains over extended considerations. Critically evaluating these algorithms requires analyzing whether local optimality translates effectively through all stages of execution. This approach shines in situations where proving global optimum feasibility proves mathematically intensive or computationally expensive otherwise. However, potential pitfalls exist, such as missing out on better overall solutions simply because early decisions were too short-sighted. Dynamic programming. Storing wisdom from past calculations. Dynamic programming emerges as another crucial methodology, leveraging previously computed information to optimize repeated computations. This strategy prevents redundant processing while maintaining reasonable memory usage. Fibonacci sequence calculations exemplify how caching intermediate values accelerates computation dramatically over naive recurrence relations. The technique works particularly well for optimization problems exhibiting overlapping subproblems characteristics. Implementers must carefully balance trade-offs between time efficiency improvements versus increased space complexity requirements. Rigorous implementation demands identifying recurring patterns within problem domains before determining viable storage mechanisms. Proper application ensures significant reductions in both runtime complexity and resource consumption during execution phases. Divide and conquer approach. Partitioning problems strategically. The divide and conquer paradigm divides larger problems recursively until reaching base cases solvable trivially. Merging those small solutions reconstructs final answers systematically. Merge sort serves as textbook demonstration showcasing O(n) log n efficiency stemming from partitioning arrays strategically before recombining sorted halves. This method excels when subproblems are independent enough to allow parallel processing. Advantages. Analyzing divide ratios critically influences resulting asymptotic behavior. Proper division sizes prevent excessive overhead costs associated with function calls. Optimal partition selection varies depending upon input size distributions, suggesting adaptive implementations might yield best outcomes occasionally. Backtracking techniques. Exploring paths through trial and error. Backtracking explores potential solution paths incrementally, abandoning dead-end trails once contradictions arise. This exhaustive search methodology guarantees finding valid outputs provided sufficient resources. Sudoku solvers represent typical implementations where systematic exploration eventually identifies correct configurations after eliminating invalid attempts. Performance characteristics depend heavily upon pruning techniques applied at various decision points along solution pathways. Effective pruning rules drastically reduce state spaces needing evaluation, making otherwise impossible problems tractable within practical limits. This approach remains vital despite exponential worst-case complexities due to numerous real-world applicabilities requiring full enumeration possibilities. Data structures selection. The foundation of algorithmic efficiency. Choosing appropriate data structures profoundly impacts algorithm effectiveness. Inefficient selections can negate even well-thought-out procedural designs completely. BSTs offer logarithmic access times, ideal for dynamic datasets subject frequent insertions/deletions. However, improper balancing leads to linear degeneracies mimicking linked lists, severely degrading performances. Evaluating operations required by algorithms provides guidance towards most compatible storage mechanisms, enhancing both speed and clarity simultaneously. Different structures excel under distinct workloads, necessitating thorough profiling before committing architectural choices permanently. Variations also influence memory footprint implications, further complicating comparative assessments, demanding careful consideration beyond mere temporal metrics alone. Amortized analysis. Seeing beyond average case scenarios, traditional Big O notation often fails, capturing nuanced realities experienced throughout algorithm lifetimes. Amortized analysis addresses these limitations, providing deeper insights regarding average costs incurred over successive executions. TREEP implementations benefit immensely from amortized perspectives, revealing true cost distributions despite occasional high-expense events appearing alarming individually. This analytical framework helps distinguish rare costly operations from regular low-cost procedures, guiding resource allocation priorities accurately. Understanding amortization clarifies why certain seemingly inefficient choices maintain competitive standing against theoretically superior alternatives practically. In practice, measuring actual runtimes alongside theoretical analyses offers safest bet, ensuring production readiness meets expectations consistently. Evaluation metrics. Measuring success objectively. Quantifying algorithm success hinges upon defining clear measurement criteria tailored specifically towards particular problem contexts rather than relying solely upon general benchmarks. Time complexity measurements capture abstract behaviors, whereas empirical testing reveals concrete runtime durations affected by hardware specifics and system loads. Benchmark suites provide standardized comparisons, although custom tests remain essential, establishing contextually relevant baselines effectively. Trade-off analyses help identify optimal compromises between competing objectives, keeping aligned with organizational goals precisely. Profiling tools assist pinpointing bottlenecks, accelerating targeted optimizations, improving perceived responsiveness notably. Real-world applications. From theory to practice, algorithmic concepts translate seamlessly into diverse industry verticals ranging from bioinformatics research to autonomous vehicle navigation systems, demonstrating universal relevance comprehensively. Financial institutions employ portfolio optimization models daily, leveraging sophisticated mathematical formulations, securing substantial returns reliably. Gaming engines utilize spatial partitioning techniques, minimizing collision detection overhead, enabling smooth gameplay experiences persistently. Healthcare analytics platforms process massive patient datasets, discovering critical correlations, transforming treatment methodologies proactively. Supply chain management relies extensively on route-finding heuristics, maximizing delivery efficiencies, decreasing operational expenditures significantly. Ethical considerations. Navigating moral landscapes as algorithm influence expands, permeating everyday lives. Ethical ramifications demand serious attention, ensuring responsible development and deployment processes occur transparently. Predictive policing systems exhibit bias risks originating from skewed historical data, potentially reinforcing discriminatory practices insidiously. Recommendation algorithms shape consumer behaviors, subtly warranting scrutiny around manipulative tendencies affecting personal autonomy adversely. Ensuring fairness amidst inherent biases requires continuous monitoring, implementing corrective measures, adaptively addressing emerging concerns swiftly. Transparency protocols promote accountability, holding creators answerable for downstream societal effects, mitigating unintended consequences appropriately. Future trends. Shaping tomorrow's computational paradigms, emerging technologies redefine traditional assumptions governing algorithm design, requiring flexible frameworks accommodating novel paradigms evolving rapidly. Quantum computing introduces fundamentally new computational capabilities, challenging classical algorithm assumptions, compelling fresh conceptualizations accordingly. Machine learning integration blurs boundaries between conventional programming approaches, suggesting hybrid models may emerge, prevailing dominantly eventually. Specialized hardware innovations drive bespoke algorithm developments, tailoring computations uniquely, matching underlying architectures precisely. Global collaboration efforts foster shared knowledge bases, accelerating discovery rates, collectively advancing human capabilities synergistically. Conclusion. Mastering algorithm design equips professionals tackling multifaceted challenges confronting digital landscapes today. Strategic combinations of established methodologies coupled with innovative thinking unlock unprecedented possibilities continually. By embracing foundational principles while remaining adaptable, facing future technological shifts, practitioners position themselves advantageously, navigating ever-evolving realms confidently.